not so important. So welcome everybody to this afternoon talk. Today we have Maria. She's the new postdoc of Eden, and she's going to essentially speak us about new directions and the model effective theory as a way to present herself to IFT. Okay, she did a PhD in Minos and Granada, and now we're happy to have her here for 3 years. No?
Yes, it goes well, I hope.
So please.
Okay,
And you can take it off your mask if you want. I will not be sitting in the first row.
should I?
If nobody is against.
Okay, thanks. So thanks a lot for having me. So today, indeed, I would like to explore some new directions in this framework. And before defining basically the tool, which will be the focus of this talk, I would like to briefly go through what is the motivation for doing this phenomenological effective field theory approach to new physics. So as we actually had before, sorry, I cannot apparently pass my slides. We're working. Okay, I don't know. Sorry, I think they, yeah, okay. So regarding the motivation for the SMEFT, we've seen this thought already here actually. And indeed, in any experimental result we're getting from the LHC, for instance, we have seen that all data agrees with the standard model prediction within red error bars, which means that in turn we have been able to push the scale of possible new physics to larger and larger values. And given this decoupling, this means we can just integrate out some possible heavy new degrees of freedom and encode its effects into the coefficients of higher dimensional operators. And this is really interesting because in this way you can really have the broadest and the most unbiased view about the ultraviolet. And the picture is really interesting already at dimension 5, because you see that we have here this Weinberg operator, which can give us neutrino masses for sufficiently large cutoff scales of around 10 to 15 GeV or so. And this is actually compatible with bound from proton decay, which would be induced, for instance, from this 4 fermion operator at dimension 6. And if you consider instead the bosonic sector, then we have these Higgs to the 6 and Higgs to the 8 operators, which can change the nature of the electric phase transition in the standard model and make its first order, which in this case happens discontinuously, and this can provide an ingredient for baryogenesis at the electric scale. And what I would like to tell you is, of course you know these, but if you assume that the SMEFT expansion should be valid up until such large scales, then we enter into some problems when we look into the renormalizable part, that is the standard model we know, because for instance we have the Higgs mass operator, and if this operator is relevant, so you would expect it to be as large as the largest scale in the theory, and then we run into problems because we actually have measured a light Higgs particle. So at the same time, although we can have some sort of decoupling regarding possible heavy physics, we have some reasons, theoretical reasons, to expect also some new physics to be close to the scale we are probing now. And it's not just this hierarchy problem, but you also have some anomalies, such as in G-2, which can be explained by light degrees of freedom. You have the strong QCD the strong problem in the QCD sector. You also have dark matter, which is in, I would say, simplest form, a winged particle, is also evidence for physics close to electric scale, as also mediators lighter than the dark matter, which can really help us if it's some bounds. And from a phenomenological perspective, you can also consider possible embeddings of the electric scale. And of course, there you can find some heavy resonances, but if you have some hierarchical parameter space, so if you have some symmetry which is spontaneously broken, you will also produce some particles which can arise next to the scale you can currently probe, and because of their unique features, they might have escape detection. So this is just a picture to explain the two directions I wanted to explore in this talk. So one is just considering the standard model degrees of freedom and its symmetries, and try to explore new effects by considering higher orders in the SMEFT expansion. And the other is really just to consider orders we have been already exploring, but perhaps adding some new light degree of freedom, which has gathered strong theoretical and experimental motivation. So this talk will be divided into these two directions. So let me start with the first one and just talk to you about what is the status of the studies in the standard model effective field theory and which directions we can extend these studies. So to the best of my knowledge, in this operator expansion, all bases up to dimension 9 of independent operators have been considered in the literature. And regarding loop corrections, so renormalization loop effects, this is known up to dimension 6. And here I will focus the discussion on even powers on this cutoff scale, just because the odd powers correspond to baryon and lepton number violating operators, and the power counting is different there because these processes are much more suppressed. So given this picture, what we wanted to ask is whether knowing this running at dimension 6 is enough, or studying the phenomenology with only dimension 6 operators was enough. And to motivate my negative answer to this question, I would like to mention some examples. So first of all, you can imagine that there are some observables, and there are some to which dimension 6 dimension 6 interactions do not contribute. And in this case, the first contributions will come from dimension 8 operators. And if these dimension 8 operators, which contribute to a given observable, are only generated at loop level by the EV, then you should actually consider also the running effect from mixing with other tree-level operators, because that's how you compare apples with apples. And another point is that some data actually allows for some large values of dimension 6 coefficients, or in other words, some small values of the cutoff scale, which means that to really be able to do power counting, we should consider the next linear corrections. And here are just some examples, of course they are not all, of studies which already indeed incorporate these dimension 8 operators at tree level. And in this paper I did together with Michael Chala, Guilherme Guedes, and Jose Santiago from the University of Granada, we were trying to explore the loop corrections to these studies. So we started computing the renormalization of the SMEFT to dimension 8. And as a first attack to the problem, we started by considering the bosonic sector. So looking into the renormalization group equations at this order at dimension 8 is particularly interesting, because it's the first order where you can actually study two colliding contributions from operators at different order in the SMEFT expansion, because you don't have a contribution from inserting in loops a single dimension 8 operator, which is this first contribution here. Wait. Sorry, I cannot point. Okay, here. But there's also a second contribution that we consider, which is from inserting 2 of dimension 6, because they will give a correction of order 1 over lambda to the 4th. And we consider this by including only the dimension 6 interactions, which could be generated at tree level from weakly coupled or normalized UV theories, which are classified here in this dictionary with this reference here. And there are two main motivations why we study from this second set of contributions. First of all, like I told you, some data seems to fit from SMEFT fits, seems to prefer some large values of these dimension 6 operators, like as you have here a result of a fit. And you can see that some operators here for Wilson coefficients of order 1 allow some new physics scales of the order of just a few GeV. So indeed they can be large, and perhaps the second set could give the leading contribution to the RGE. But the main motivation is that there are actually some non-renormalization theorems which are known for this first set here. So although people have not computed the RGEs for this first set, these theorems from I think on-shell methods allows you to know what kind of mixing structure you would expect from this first set, and no results up to date exist, or until we publish this work for this sector here, exists for knowing the structure of mixing from the second contribution. So this is what we wanted to study. Let me go through a bit the details of the calculation. So to consider this problem, we had, of course, to get the divergent amplitudes at one loop. And this we did by considering the irreducible diagrams by putting our Lagrangian in fine rules, then drawing the diagrams with fine arcs, and finally extracting the one loop divergent amplitudes with form calc. And we did some manual checks with other programs, using other programs as well. And after fixing this divergent amplitude, what we did was matching to the off-shell basis, which comprises all operators, which are independent upon the use of integration by parts and some group identities. And in many cases, like this one of dimension 8, this off-shell basis is not known, and sometimes it's not a trivial task to build it. As for example, in this class of operators here, Higgs 4d4, you have like 13 interactions only in this redundant basis, and among these, only 3 are independent when we go on shell. And another effect we have to consider is that not only we have to consider loop diagrams with 2 insertions of dimension 6 operators, but we also have to match to the off-shell basis at dimension 6, considering only an insertion of a dimension 6 operator. And that's because when you use field redefinitions, from these dimension 6 redundant operators, you will get contributions to the dimension equivalent. And we had to do this by scratch because these contributions in the off-shell basis in the literature were not known even at dimension 6. So another thing I wanted to mention is that I'm saying that here we are removing operators with field redefinitions, but we can also do it with the equation of motion. But that is true only up to linear order in the perturbation. That is, imagine you want to remove some operator of dimension 6, and you do some field redefinition like this, where here x is what I call the perturbation. And then you have to match to a redundant operator, which was already fixed by some divergent amplitude. So this counter term is already 1 loop level. So although in general, you cannot actually use the equation of motion to get this quadratic order on the perturbation that we need, because we want to keep effects of order 1 over lambda to the 4. Here we can actually just use the equation of motion because we are not interested in these corrections because they are formally 2 loop. That is the only comment I wanted to make here. And then given this, if there are no questions, I can just resume what is our theoretical setup and our results here. So like I told you, we are considering dimension 6 interactions, which can be generated at tree level by the EV. And this comprises a set of 3 operators involving only Higgs and derivatives here, plus another 5, which involves Higgs and fermionic fields. And once you put these operators at the loop level, you can actually generate this class of dimension 8 operators here. So for instance, if you insert 2 Higgs to the 6, you produce a Higgs to the 8 and so on and so forth. Of course, you can either produce Higgs to the 8, Higgs to the 6, or Higgs to the 4 operators with derivative and field strength tensors. And given this, I won't bother you anymore with details of the calculations, and I just wanted to show you some results. So here I'm just showing you the structure of the anomalous dimension matrices for some cases, for some particular cases of operators, which are defined always here below. And you can see that there are many zeros, just because, for instance, we cannot build diagrams using some combination of dimension 6 couplings. And here the cross denotes entries which are non-vanishing. And here there are these particular zeros I wanted to mention, represented by this empty set here, which we cannot trivially understand because they are non-zero in the redundant basis, and they just go to 0 when we go on shell. And this is really interesting when you can consider even other operators, which seem to have some diagrams present in the redundant basis, but they go to a matrix which is completely vanishing when you go on shell with no apparent reason as far as we could realize. And this has important implications for the phenomenology, these 2 operators in particular. So let me now explore some of the consequences of these results. So first of all, what we find is that the operators, which are renormalized, arise at tree level in UV completions. All the dimension 8 operators that we get from considering the insertion of dimension 6 tree level operators also arise at tree level. And this is something I wanted to mention because this is what we wouldn't expect this by considering these non-renormalization or renormalization theorems, which exist for the contribution from the dimension 8 operators alone to the RGE of the dimension 8. Because what you see from these theorems is that there is generically mixing from tree and loop level operators as represented here in this lattice. Another consequence that we could realize is that when we consider correction to these precision electroweak parameters, So for the S parameter, we already have corrections at dimension 6 as computed in this reference here. But the corrections come with this O5WB operator, which is also only generated at loop level by renormalizable weakly coupled UV theories. And what if we find at dimension 8 is another contribution, this operator here, defined below, the WB54, and again, this is only generated at loop level. So we find out that still this conclusion that this parameter is now renormalized by tree-level dimension 6 interaction holds when we consider corrections at order lambda to the 4th. For the U parameter, actually, the corrections start at dimension 8, but again, they come with an operator that is not renormalized by the dimension 6 interactions. So these operators here, the WB1 and the W squared 3, are exactly these ones which have a completely vanishing anomalous dimension matrix. Another consequence we could explore was the impact of this dimension 8 running to the electric phase transition. So here we are computing the corrections to the Higgs potential, assuming that the only effective coefficient, which is non-vanishing, is the one associated to the Higgs to the 6 operator, so this C5. So you have here the standard model, then you have this operator, this effective operator at dimension 6. It's running as computed by Manohar and collaborators, and then this contribution from this work from inserting in loops 2 contributions of these Higgs to the 6. And what we find is that when we study the conditions to have an electric phase transition that is strong in first order, which is the one that we really care about, for instance, to make baryogenesis. So this strong condition is to avoid washout after we make some asymmetry during a first order phase transition. And we find that the Wilson coefficient compatible with such strong phase transition is actually, it changes with the inclusion of this running. And in the upper limit, the corrections are 30%, which is a lot. So this really says a bit, this really says a lot on the potential of including both dimension 8 interactions and their running. And finally, I wanted to discuss a bit the interplay between positivity bounds and the results that we get. Because, some fundamental principles of quantum field theory, like locality and unitarity, they give us this condition on the second derivative of the forward amplitude relatively to the transfer momentum squared. And as the coefficients of dimension 8 operators enter into this condition when we compute this amplitude, this basically delimits the SMEFT landscape in the sense that other EFTs with coefficients which do not lead to this condition, which do not comply with this condition, cannot be UV completed. And this is very interesting because we can look at this, or we thought we could look at this in 2 ways. One, to basically shrink the parameter space we have to include in some SMEFT fits from requiring this theoretical consistency, or you can just think that we are agnostic about this. We measure some process at the LHC that is sensitive to the dimension 8 operators, and by studying their signal, we could understand this fundamental core of conditions in quantum field theory. And the way we can have access and infer something on these positivity bounds, this comes from the fact, before going into my problem, I forgot I had this slide to say a little bit more of how you derive these bounds at tree level. Sorry, so here you can consider some scattering of Higgs components. And if you study the forward amplitude when you're scattering phi 1, phi 2 to phi 1, phi 2, you see that you have a contribution from the standard model, this lambda here, the quartic coupling of the Higgs. Then by dimensional analysis, you would expect some contribution of dimension 6 operators and then dimension 8 and so on. What happens is that we are, first of all, this forward amplitude has some symmetry, which is an invariance when S goes to minus S. So there is no contribution here from dimension 6. This goes away. And of course, since we are interested in the second derivative for these positivity bounds with respect to S, the standard model does not play here any role. So you only have, in this case, scattering these components. You are only sensitive to this C2, which is defined here below as the second operator in the class Higgs to the fourth, d to the fourth. And if you actually scatter other components, you can derive the other conditions, which is that C1 plus C2 also need to be non-negative as the contribution of C1 plus C2 plus C3. So this is basically what has been found at tree level. What happens at loop level? Well, we could have access to these exactly because we have computed the vector functions of these Wilson coefficients. And what you see here is very interesting. Like if you consider the vector function of the second of these Wilson coefficients, which alone is subject to this condition, what you see is that so in the bosonic set, without fermions here, you can form perfect squares, and so you have an overall minus sign. And the same for here, the fermionic contribution. So this vector function is entirely negative with irrespectively of the signs of the dimension 6 coefficients. So if you imagine that in the UV, this Wilson coefficient is 0, you're only running down into the positivity region. So this is completely positive. And when you actually consider the sum of C1 plus C2 and the sum of this vector function, this vector functions is really interesting because a priori this vector function 1 could be negative. However, there's here a delicate cancellation of terms, which really guarantees that you're only entering by the running into this positivity region. So indeed, regardless of the sign of the dimension 6 coefficient, positivity is maintained at loop level by these dimension 6 interactions. After our work, however, Michael, Talan, Jose, Santiago, they continue to study this problem to see if this should hold always at, in this case, at one loop level. And they found many counterexamples. Like, if you're just considering extending the standard model with a new singlet, this particular UV, then you compute the matching at tree level to the operators, and you see that indeed positivity in these coefficients is maintained. Because C2 is 0, C1 plus C2 is 0, and the sum of the 3 is positive. However, at loop level, you see that already this is broken. So this C2, which at tree level needs to be non-negative, here it picks a minus sign. So this is violated. What they also did was start the computation of the renormalization group running, not from the insertion of 2 dimension 6 operators, which was what we did, but from inserting only 1 dimension 8 operator. And they found that, again, this running triggered by the dimension 8 operators also brings us away from the positivity region. This does not mean, of course, that this condition here is violated. It just means that the impact on the Wilson coefficient of dimension 8 is somehow different. And they give reasons for that in their paper. I won't spend much time on this, but basically this has to do with defining an organized perturbative expansion in the forward amplitude. And basically when you see that at tree level, some of the coefficients that are important for these positivity bounds, if sum is 0, and so you start picking up some loop effects and mixing with other tree level effects, then it's not true that this positivity on the amplitude translates into positivity on the Wilson coefficients at dimension 8, because you can be dominated, for instance, by the running of the standard model such that the amplitude second derivative is positive, irregardless of the sign of the anomalous dimensions. And that's how they explore these for different conclusions of the standard model, showing that indeed you can go away using this running. You can go away from the positivity region. However, what is shown is that indeed the positivity is maintained by the running due to only dimension 6 interactions, which is a really important cross-check of our results or any other results that are performed in this direction. And I finally wanted to mention regarding this work something which I think is also interesting. I told you that we have all these non-trivial zeros, which we cannot understand. So perhaps they give this argument. If you imagine, let's restrict ourselves to just 2 by 2 matrices to see what could be happening here. And if you imagine that so these dimension 6 coefficients could take either sign, an arbitrary sign, and for some reason, like we saw in some cases, you have some trivial zeros, so you just cannot build diagrams involving these dimension 6 interactions. So let's assume that gamma 1, 1 and gamma 2, 2 are 0. Then these trivial zeros could imply a non-trivial 0 here if there is some positivity hidden in the C8 coefficient that we don't know. So perhaps there is some positivity related to operators which are not in this class, which has been explored a lot, the Higgs 4 before, and maybe in this class of field strength tensors and derivatives, we can also find there some positivity theorems. So this is a direction that definitely I would like to explore, and they would like to explore too. Okay, but this was what I wanted to say about this SMEFT at dimension 8. Now I wanted to evolve to another topic, expanding the SMEFT with other light degrees of freedom. But I would ask here maybe if there are some questions regarding the previous topic. No, I will.
You were talking about the renormalization of the dimension 6 operators. You have dimension 6 operators that you generate, let's say, at tree level. You square them, you take dimension 8 operators, but you said you have to renormalize the dimension 6 operators. Understood you correctly?
No, I was considering the dimension 6 to renormalize the dimension 8 operators. So I was talking about renormalization in the dimension 8 sector.
Okay, so you don't renormalize the dimension 6 operators.
This was computed already, so we were just trying to go to the renormalization at the higher order.
Okay. So what you are computing is that the renormalization of the dimension 6 operators affects the renormalization of the dimension 8.
Yes, they're running triggered by the dimension 6.
And to me, what is the obvious conclusion from all this study is that the real counting of the SMEFT should not be done at the level of operators, but at the level of observables, because at the end, they mix at the same counting in the observable. And in the contribution from the dimension 6 and the dimension 8, they go together and they contribute with the same counting in terms of lambda to the denominator to the real relevant thing, which is the observable. So it's like another way to understand the counting of the SMEFT, not only in terms of operators, but in terms of their contribution to the running and at the same time to the observable. So it's like saying that there is a different counting, an additional counting to the usual one in terms of operators. Yeah, they all contribute. They all, the dimension 6, the normalization of the dimension 6, they contribute to the normalization of the dimension 8. And at the end, they mix both in the normalization of the equations and in the contribution to the observable.
Yes,
But this effect of dimension 6 into one observable contributes at the same level as the dimension.
of course, it's a higher order effect than just looking into lambda to the lambda square correction. But yes, like people in some feats, they are doing already quadratic corrections of dimension 6, and then it's not correct to neglect dimension.
What's up is very controversial. We are young boys. I would like to have participated in that discussion. There is always underlying the discussion. What is the thing that you should count? Is the cross section? Is the amplitude? Is the effective operator? You count. What is the dominant when you count? And in this discussion, you have to say what is the dominant. So if you count on sigma on the cross section, there is the amplitude squared. So all the contributions, the products of these two times this contribute, and there is always this controversy. There is the controversy when you read papers from NABLA, CMS, in the interpretation of the constraints to the Wilson coefficients. There is always this controversy. I don't know how it's at this moment, maybe you can know, but when they conclude on constraints of the Wilson coefficients from data, there is always this mismatch. Are you computing from the cross-section space or the counting from the amplitude? You know what I mean? Are you squaring the dimension 6 and considering at the same time dimension 8, for instance? In the extraction of constraints. It was a very controversial issue. And as far as I remember, when I listened to the talks by these people, they always put two columns. One is you interpret cross-section, or you do the counting at the amplitude. In other words, squaring or not squaring. In the figure, you know what I mean?
Yes.
And the answer is different. The answer on the constraints on the Wilson coefficients is quite different.
Here our problem. Here our problem was a bit more defined because we were just computing at all contributions of order 1 over lambda to the 4.
But to what? Lambda to the 4, to the amplitude, to the cross section, to the Wilson coefficient.
superficial. Yeah, I know what you mean. I'm just defining the problem. But yes, sometimes people argue like when you interfere with the standard model, maybe you can neglect its contributions and you keep only the quadratic ones. But yes, I see your point. Yes. Yes. No, go ahead, please. We can continue also afterwards. Okay, but if there are no urgent questions, I can move on to the second topic, in which we were trying to extend the model, the SMEFT, with some light candidates which have rather strong theoretical and experimental interests. And here, there are many specialists around because I'm going to talk about axion-like particles. And I gave this slide as a motivation before to why we can consider or expect some new degrees of freedom in spite of some decoupling with other heavy ones. And of course, the ELP is really motivated because it can appear in all these problems. It can be dark matter. It's also an excellent light dark matter mediator, because if you assume that CP exists in your scalar theory, then the fact that the ELP is CP can bring contributions to direct detection at foot level, which really helps us if it abounds. It can also be a solution to G-2 and other anomalies, solve the strong CP problem for some relation of decay constant and mass. And from a theoretical perspective, considering embeddings of the electric sector, it appears in many models, and if you consider basically all symmetry patterns, it's very common that you produce singlets. So there is lots of motivation for this axion-like particle, which here I define just as a pseudoscalar singlet, nothing else, keeping it general. And from experimental perspective, there's also a huge effort to search for ALPs. So here are some bounds that span really several orders of magnitude in the ALP's mass. And at the electric scale, you could think about producing it in PP collisions, but its interactions are very suppressed because it's a gauge singlet. You could produce it by an off-shell Higgs particle, but then the cross-section is very suppressed. And even at 100 TeV collider, apparently, the bound would be very weak. So this is a motivation also to consider it's beyond renormalizable Lagrangian, exactly because our renormalizable level is very inert.
Maria, question. With the pseudoscalar singlet, are you in any case taking on derivative couplings?
No,
It's completely
completely general.
CP both
Yes.
Singlet.
Singlet. This is our framework. You see, so you have here everything you can write, assuming only that the UV is CP even. So we are considering this sector in isolation.
Okay.
And even thinking about it as a pseudo-Gaussian particle from the perspective of many models like composite Higgs, even studio, I would say. Once you have some explicit interaction that generates the mass, then the same interaction, for instance, in composite Higgs model, will generate this quartic coupling. So we are keeping everything here, even for the case of a pseudo-Gaussian particle. No? And at dimension 5, we organize here the operators in these different classes that are called Yukawa, derivative, and gauge. So here we have the interactions with the Higgs boson in this sector here. Then we have these operators with the derivative, which of course, by employing equations of motion, you can relate to these ones. So these operators here are redundant and only transforming these ones when you use some Hilbert definitions. And then you have these operators of the ALP interacting with the gauge bosons. Okay, and here again, we are not mentioning any condition to make these interactions shift invariant. Okay, so I won't go into many details here because the computation is the same as before. So what we have to do, for instance, if you consider the divergent contributions or the one-loop contributions to the Yukawa operator with the electrons, what you have is contributions from inserting the coefficient itself. You have also contributions from inserting the ALP coupling to bosons. And not only this, but when we are matching off shell, you see that you also generate contributions to the S phi operator defined here. So phi to derivatives and another phi plus an ALP. And these contributions here, of course, they have to be flavor universal. So when we use the equations of motion to transform it in a contribution to the operator we want, they have to be to take this weight of a Yukawa matrix, basically. So in the end, skipping this and going to the results, this is the anomalous dimension we get from this generic Lagrangian. And I have to say, many of these results were already in the literature. The phenomenology of ALPs has been explored a lot. There were some contributions missing, like these quartic operators, which should be there for the case of a generic pseudoscalar singlet and so on. But I will mention some comparison with the literature after this slide too. Here is an example just showing the limit in which the different families factorize. That's why in the Yukawas we only have one index. But you can see that even though you consider this limit, there is some intergenerational mixing from these traces that appear from considering contributions to these redundant Higgs and alpha operators. So what we see here is that in the upper part of the matrix, everything mixes up to this trivial zero, which is due to the fact that, of course, leptons are not H3 charges, so they do, the mixing from these operators here is not present with the gluon. However, in the bottom part, the results are very different, and you see lots of zeros, and basically we see that these gauge operators with an ALP only run proportional to themselves. And this was something that we already know a priori, because there are these non-renormalization theorems derived with on-shell methods at one loop, so we could cross-check. And what happens here is even more interesting, because once you factorize out the gauge coupling, you see that you would get zeros here everywhere. So this running is only due to the running of the gauge couplings themselves. So I will come back to here, but now I wanted to move on and tell you something about comparison with other bases, like the explicitly shift invariant basis, which has been used commonly in the literature to connect more with the case of a pure axion. And if we compare, we have here these common used bases for the case with only couplings to leptons to facilitate our reasoning here. In comparison to the basis we use, and here we are, this is the CP preserving interactions. So here for these, to have this CP condition, this A matrix that we get, this flavor matrix has 9 parameters. And here if you consider also CP violating interactions, you have +9. And this is the same counting that you get in this basis because these are emission matrices. And this seems okay. It's 18 versus 18. However, one includes only shift invariant interactions, while the other, the one we use, includes both shift symmetric and shift breaking interactions. So there should be some redundancy here. And this has been a lot explored by Neubert and collaborators, Beleng and Bonilla, which is around, and they have been exploring a lot of these. I just wanted to comment that one way to see this clearly is that using this equation here, where the A and H matrices are defined here below, you can see that under some conditions, indeed, the left-handed and right-handed couplings can be traded by one another. This is true, for instance, if you are in the limit of one of the ALP coupling only to one family, or having only diagonal couplings, in which case this A matrix goes to 0, and you see that these left-handed and right-handed couplings are entirely related. And so if you want a minimal basis, you can remove one. And the same holds for the Fock sector. And we actually assume that just to have a way to really move easily between bases, because if you assume these minimal sets, then you actually have a one-to-one relation, let's say, between the parameters in our bases and the parameters in the bases often used, these CE matrices. And we could relate them in order to, knowing the running we have computed, and of course, knowing the running of the Yukawas in the standard model, we could just cross-check with some results in the purely shift symmetric basis. And I just wanted to comment something that was also cross-checked, which is that when you consider the multiplicative running of this coupling C, you see that there are not contributions which go with the gauge coupling square, which could be here as well. And that's just because at this order in gauge couplings, you still don't see the anomaly of this current. And so you see something that if you don't see the anomaly, this current is at this order, this current U1 here is conserved, and so it is a result that conserved currents are not renormalized off shell, and that's how this explains the fact that you don't see here the G square contribution. But this is not true when you go to higher orders in loops, for instance. And this was computed, for instance, in this reference here, that when you go to higher orders and also consider, you start seeing, so at order alpha square, so g to the 4, you start seeing the anomaly of the current. So you need to have at higher loops something here involving also the fermionic couplings. So this contribution here corresponds to loop contribution. And we know that this actually needs to be there at some point, and it happens at order alpha square, because this is really the contribution that remains invariant under rotating with the global symmetries of the standard model. And this is discussed in this paper here in more detail. Finally, to conclude this point, I also wanted to discuss with you the running in the low energy EFT. So at some point, we have to integrate out to maintain the validity of the EFT. We need to integrate out the top, the Higgs, the W, and the Z boson. And as we go down in energy and past some fermionic thresholds, we should keep integrating the fermions as we need them. And we constructed this low energy effective field theory with an ALP up to dimension 5, keeping the framework general, so considering all the interactions which could arise. So you have here a dimension 4 ALP interaction with fermions in this left. You have again the interaction, dimension 5 interaction with Higgs bosons, now the photon and the gluon, which was already present in the high energy FT. And then you have also the purely SMEFT dipole operators, as well as an interaction with the fermions and the ALP at dimension 5. These terms here in the last line are actually higher order if you consider that at the electroweak scale, you have only the standard model plus an ALP. And you can see this, for instance, from knowing that this S-squared side coupling comes from integrating out a Higgs boson, which seems to be apparently order of the correct order 1 over the VEV. However, knowing that this Higgs is the one that sets the light fermion, the fermion's mass, you see that this is actually order V to the square, and so is not there if you assume that the UV is just a standard model of the ALP and the ALP. However, we wanted to keep it general because just imagine you have another Higgs doublet, then this term is there to begin with. Okay, so exploring some effects here, some new thing that we see in the low energy EFT is that there is mixing of operators which are of different mass dimension in the Lagrangian. This is something that we didn't see in the high energy FT for symmetry reasons. I don't know if I have time for these 2 slides. So this is just show that we would expect some contribution to begin with from this redundant operator here, which is psi bar d squared psi, so purely SMEFT. But when you use equations of motion, not only you have contributions to the ALP Lagrangian, to the ALP couplings, but also to the wave function normalization of the fermions. So we would expect that this wave function factor will have also dimension 5 contributions. And so these effects would propagate basically to any renormalizable coupling, to the renormalization of any renormalizable coupling involving the fermions, just from this fact. But this is not true actually, because you can show that if you integrate by parts your term first and you have a different contribution, then this dimension 5 contribution is completely cancelled out, because you can actually rotate the fields, do Carroll unitarity transformations to remove these. So this part here is actually not physical. But you do have some direct contributions when plugging in effective operators in loops, which going with the mass of the fermions or with the mass of the ALP, they can renormalize other dimension 4 contributions. No problem. So you have this effect that, for instance, mass of fermions are renormalized by the mass of the ALP and vice versa with the proper insertions of mass. To conclude, we also see this effect in the low energy FT, which is that the couplings of the ALP to the Higgs bosons, in this case, they do run the same. So this RGE here is exactly the same for the operator with the gluon, except that you have some new contributions from the dipole operators involving the gluon itself. And I wanted to make a big sense of this. I don't know if my reasoning is correct, but to understand this kind of non-renormalization result in the high energy FT and the renormalization in the left. So one thing that is useful, I think, is to consider first the limit when the ALP is decoupled from the fermions, because that is a limit that you should be able to see in the high energy effective field theory. No? And if you do that and you consider the coupling to the gauge bosons, and you assume that you are in the limit of a pure axion, a periodic field, and you have this decoupling. So if you require that indeed your symmetry, that the ALP shifts by 2 pi is respected, then you need to require that this CF coupling is quantized. And that's it. That is because when you do this shift with 2 pi, you know that when you integrate over the space-time, this alpha x tilde with proper loop factors is actually a topological charge, is an integer. So you do get rid of this term with no physical consequences if you require that this CF is an integer. And that matches the expectation that if you are decoupled from the fermions, then indeed you should get this non-renormalization result, I think. On the other hand, when you turn on the interactions with fermions, things get messier, especially if you have terms like this C coupling, which is an ALP coupling to psi, which you can see that it comes from this exponential when you expand. And when you do that, you see that actually is not this CF that is quantized, but it's a combination with this CF and other couplings, which is discussed in detail in this reference by Fraser and Rees. So I think this makes more sense regarding the renormalization, non-renormalization of this kind of couplings. I don't know if you would agree. So finally, I just wanted to show you some phenomenological consequences also for this case. So basically compare which kind of limits we get by studying these RG constraints. So here we just assume some photophobic model in the EV. And this kind of photophobic behavior you can have in some frameworks. You get this term here from the next to minimal composite Higgs model, for instance. And when you run down this coupling to the electric scale, you see below the electric scale, there is no coupling with a photon. And that is not generated in the left because you see these kind of dipole operators here are not generated if the UV up to dimension 5, if the UV is just a standard model for the alpha. But if you have more complicated, a more complicated spectrum, actually, you can get the running in the left, even though you don't have it in the UV. And this is an important effect because this coupling is really, really constrained. And okay, so from this photophobic Lagrangian, assuming just a standard model and the ALP, we took some direct constraints that were, for instance, presented in this paper here, which show that at the higher luminosity LHC, you could reach, studying PP going to a Z boson and ALP, you could probe some AZ coupling of the order of 10 to minus 2 in units of the TV. However, you know, from the renormalization group equations, we know that if these couplings here to the gauge bosons are present in the UV, you will generate other things besides the coupling itself. And that's why it is so important to know these evolution equations. In particular, we generate the ALP coupling to electrons, which if you assume that the ALP is sufficiently light, then is tightly constrained by these astrophysical bounds. In this particular case, the most constraining bound is from red giant's cooling, which is not observed if there is not a sufficient. So if the stars would emit lots of ALPs, then you would see some difference in the cooling of the stars, and that's from where the bound comes. So we can just study how this bound at the Keavy scale evolves, or in other words, what is the coupling here, this ASZ coupling that matches this bound at low energy. So we study that, and the indirect bound we get is 4 orders of magnitude different, stronger than this direct bound. Of course, this cannot be taken at face value. It's not so strong as framing a direct bound, but is important when we are constraining a particular UV completion and should be considered. And just to mention also, because I think this effect was considering for the first time here, we also include the running in the pure low energy effective field theory, and the effect is small. However, we evaluate these, and it can just be used as some systematic error in future computations. finally, to give another example, we also consider a top Felix scenario. So now you assume that in the UV, the only coupling you have with the ALP and the standard model is via top quarks. And here we were assuming that this coupling generates a 10 TeV, and we again study what are the indirect bounds we would get from this bound I just mentioned from red giants applicable to a light ALP. And we do have a similar bound as before, so 10 to minus 6, which is again much stronger than typical bounds from PP collisions, which are very challenging when you consider top quarks in the final state. And this is a study found here in this paper where the same reasoning is applied, but over a larger parameter space regarding the mass of the ALP and considering different probes. So the bound is of the same order of magnitude, but it can be slightly stronger when you consider also bounds from xenon 1 ton. So this is really a complementary way to study the constraints and should really indeed be incorporated in the phenomenological studies. And that's all I wanted to say. So thanks a lot for having me.
Thanks a lot for a nice talk. Time for questions or comments.
Yes.
Yeah.
This way.
For the second part, have you considered the consequences if you go to the axion case? But not only, I mean, you were discussing the axion case a little bit with the periodic potential. But the axion that solves the PCB problem, it maybe is even responsible for dark matter, which will constrain the parameters for your coefficients in the multi. Consider the possible consequences.
Considering that it is a dark matter, you mean?
Yes.
Or no, we didn't study that.
And this would be a real, I think the nice thing about the axion is that you can use it as a dark matter particle. And for me, this is one nice motivation on top of the original one, which of course with the ALP is also possible. Now, but since you mentioned that we were considering at least the periodic potential and the consequences.
Yeah,
then, okay, I asked my question, you said you didn't do it.
No. So we just wanted to compare with these bases that appears often in the literature that is more connected with the axion, but it's also not for the axion itself because the axion requires a particular relation between mass and couplings.
Exactly.
Yeah, but I don't know if there are some studies plugging in these indirect bounds. In that case, that would be interesting, but I'm not aware. I don't know if anyone knows. But I don't.
I mean, the basis that you can construct can be for on alpha or axion. The only difference between the two is the mass that you're taking.
Yeah.
If you're taking a very large mass, then in principle you're violating the sheet symmetry. But as far as the mass is sufficiently light, the basis that you write is an alpha, a light alpha, let's say, up to 1 GeV, 10 GeV, down there, down to axion mass ranges.
Yeah, so the basis is really the same, but I don't know if someone has explored the consequences of the running.
The analysis depends. If you go looking, if you use the basis and you go looking to collider bounds, for example, typically you take GV values for the alpha in this case. This is a comment that I wanted to do in the not the previous, but the next previous slide.
Yeah.
In the previous one, the bounds that we got there. The coupling AS that field is for 1 GeV alpha.
Yeah.
So the bound that you're putting there at 2 minus 6 corresponds to an alpha that is much lighter.
Yes.
That is the one where the coupling to the electron applies. So in this case, it's not a comparison between the two limits. It's the same line limit, but for different values of the masses of the alpha.
Yeah, but if I'm remembering correctly, this and well, because you did it, but I thought you were just referring that the ALP was invisible in the detector, at least in some of the
We
analysis.
consider the two situations.
And I don't think that was dependent on the mass.
Depending on the mass, of course, because if it's too heavy, it decays immediately in the detector.
Yes.
But in this specific case, in which we did the analysis, it was sufficiently long-lived not to keep signals in the detector. So it was, the detector has some meters of length, and it was decaying after it. So
But
it was
here-
invisible to the detector.
Okay, but here we were if we put the light, the out a little bit lighter,
It will be visible.
so it would still apply the bound, no? Because here we are considering TeV scale. That's why we took the bound.
No, because in this case, you have the bound from the coupling with electrons. But if you take 1 GeV alpha, then this bound doesn't apply to it.
No. Sure, okay. But if you imagine, okay.
So it's not taking one bound that you can extrapolate to whatever mass. If the delta has a specific mass, and to this mass, there are some bounds that apply and others that doesn't.
Sure.
This is an indirect bound from the coupling to electrons. But if the delta is a 1 GeV mass, then this coupling doesn't apply. So equivalently, your induced bound doesn't apply. That is why I'm saying that we could put a bound in a plot of the bound on A as Z in function
As a
of the
function
mass.
of the mass.
And then you would have a different values, much higher in your case with lower masses, and it goes down at higher masses.
But anyways, we were assuming here still that the coupling to electrons would be sufficiently small for it to not decay. For this
Yeah, but
mass.
the mass is enough not to decay.
Yes.
It would be visible in any case. But yes, regarding going back, the basis is the same. It's just the type analysis you do. You can take this basis and maybe, for example, applying to flavor physics. And there, for example, if there would be some mediation of flavor effects, the bound will be extremely high on the scale, and this would be true as well for an axion that is very high. The physics is invisible. Other questions, comments?
Have you done other consequences for manufacturing your units of the cells that you find in the data?
You mean if
You
they are
are saying that you find a lot of zeros in this big matrices. Have you studied
this exploration of new positivity bounds? No, I am about to, because, but it's not, first I would have to, so the way they are computed, the way they are given is for these 2-to-2 scattering processes. And for getting these bounds for the kind of operators we get, because before we had 544, which means that you can compute the scattering the SMEFT. But now we have 2 field strength tensors and 4 Higgses, which means that to compute this 2-to-2 scattering, which is how I've seen this, you have to go to the broken phase. So I still have to reproduce to know if indeed I can get some results of positivity in this broken phase, and then I would evolve to getting to know something. But not yet, no.
Other comments? Question? Right, so I think that we can thank again the speaker. Thanks to Maria. And welcome to today.
No one was in the Zoom, right?
I'm stopping. Yes.
I understand.